Hi class, this last section of Chapter 5 is kind of a long one, so there's a lot of information here, but it wraps up all the ideas of the chapter. So we've talked about how atoms give off light, how matter is made of atoms, and those atoms ultimately can give off light, they can absorb light, and so on. And every atom has a certain fingerprint in a sense. Every atom can give off or emit only certain wavelengths of light. So how does that tell us things about stars and such, galaxies in the sky? What can we, how can we measure galaxies and stars in terms of like what they're made of, or what their temperature is, or how fast they're moving away from us or toward us? All these things we can actually measure by looking at the starlight, at the actual light given off by the objects. So when we look at a spectrum, an overall spectrum of something, we see often a combination of things, but we can break the spectrum down into three different classes of spectra. So this figure you're looking at right here is a little complicated, but the idea is that what you're plotting is the brightness as a function of color or wavelength. In other words, you're looking at the light coming from some object, and you're seeing that there's a lot of red in there. It's a very red object. But then as you go into the infrared, it starts to get dimmer and dimmer. And then as you get further into the infrared, at some point it gets brighter again. But there's a couple places here where there's less brightness, but then it's brighter. So there's an area in the infrared where it's a pretty bright object. It's also bright in the red, too. It's kind of dim in the blue, right? It's not very bright in the blue. So this object looks actually probably red to our eyes. We can't see the infrared, so we can't see that. But so the object definitely probably looks red, not very blue. The blue light has been kind of somehow absorbed, maybe, or it doesn't exist. It's not coming from the object. And then there's also these interesting features where suddenly we have some quick, short little kind of bursts of brightness in a sense for particular wavelengths in the ultraviolet. So that's kind of interesting too. So when we look at an object and we look at the light it gives off and we really break it down into the different colors and we plot the brightness of the different colors as a function of the wavelength, we see what we call a spectrum. And we compare different objects and we look at different spectra. So how can this tell us about the object? How can this thing tell us the temperature of the object, what the object is made of, maybe? Well, we'll come back to the spectrum in a little bit. So these are the three basic types of spectra. Continuous spectrum, you see basically all the colors of the rainbow, and that's formed by just sending white light that might be created by a light bulb or some hot solid object perhaps through a prism, and that white light gets broken into all the different colors of the rainbow. It's a continuous spectrum, there's no gaps. And so the brightness as a function of wavelength is a continuous curve, and there's a peak in a particular place, there's a particular wavelength that's the brightest. An emission line spectrum is like what we talked about with what atoms give off. If you have a cloud of gas, a gas that isn't like a really, really dense, but it's a fairly diffuse cloud of gas, and you somehow excite it, it will give off particular colors. And so if we look at those colors, let that light go through a prism, and that prism will break up that light into its different colors, we don't see a continuous spectrum. We see just certain particular colors that are emitted by the object. That's called an emission spectrum. And then if you take white light that has all the colors of the rainbow and send it through a cloud of gas, that cloud of gas is going to absorb anything that it can emit. All right, so atoms that can emit certain colors can also absorb those colors. And so what you'll see coming out of the cloud of gas is the continuous spectrum of the light, but you're missing some colors because of the absorption from the gas. Now, this absorption, if you look, for example, here, the absorption doesn't make the brightness of that color go all the way to zero. But relatively speaking, this line looks dark. It looks dark in here. But there really is some color of this particular wavelength coming out. It's not all absorbed, but a lot of it is absorbed because the gas is absorbing it. If this cloud were more dense, it would absorb more of that light. But also, because the gas absorbs and emits the same colors, if a cloud absorbs one of these colors, for example this one, it can also just re-emit it immediately. And it's possible that re-emitted light can come right back toward the prism. And that's another reason why this line isn't completely dark, because there could be some light of this particular color still coming from that cloud, because a cloud of gas will emit any color that it also absorbs. So there's a little interactive figure. We can look at this a little more closely. So it shows you here the different spectra: continuous spectrum, emission line spectrum, and the absorption line spectrum. If you click on each of these, click on show, it shows you a little animation. There's the white light coming out of the prism, coming out of the light bulb, goes through the prism, and we see a nice continuous spectrum of colors. And we can look at what happens if we adjust the temperature of that light bulb. As you increase the temperature of the light bulb, it gives off brighter and brighter and brighter colors. Notice this curve is getting taller everywhere, but it's also getting taller even more in the blue and the purple area. So as something gets hotter and hotter and hotter, it's going to give off all the different colors of the rainbow, but it's going to give off more and more and more of the colors on the purple and blue side of the spectrum. So a really hot object is actually going to look kind of blue. It'll give off a lot of red light too, but it'll have a blue tint to it because it gives off more blue light than it does red light. On the other hand, if it's really cool, it doesn't give off a lot of blue light, it gives off more red light. And so if it's a fairly cool object, it's going to look more red. So stars that are cool look more red, stars that are hot look more blue. Going back to the main screen, we can click on the emission line spectrum, show that. So here we show just light simply coming from a cloud of gas. Light that just comes from a cloud of gas shows just the colors that the gases of that cloud will emit. And so this might be hydrogen. It gives off a particular red color, a particular bluish green color, and some purpley colors here. And those are the particular visible light colors that a hydrogen gas gives off. And that's an emission spectrum. We can show the details here, and what it's showing is that there's a cloud of gas giving off, you see these little gas atoms, they really should be kind of floating around in here, but they're each giving off a color, and they go off in random directions. And these colors could head ultimately toward our prism, and we could show that on a screen or something and show an emission spectrum. If we hide the details, we can also change the gas to, instead of hydrogen, we can look at neon. And there's the spectrum of neon. Neon is a much more complicated atom, so it gives off many different colors than hydrogen gives off, but it's still an emission spectrum. You still don't see a continuous sort of range of colors that it gives off. Going back to the main screen, we also see the absorption spectrum. So now we're going to shine white light from a light bulb through a gas. Some of that light will get absorbed, and we'll see gaps in the continuous spectrum. And again, as we increase the brightness of the temperature of the light bulb, all that sort of continuous spectrum gets bigger, and we still have these absorptions going on because of the gas. But not everything is absorbed. This intensity at this particular wavelength doesn't go all the way to zero, because there is some light that does get through the gas, that does get directly through the gas, and also the gas itself is emitting that particular color in random directions, sometimes toward our prism. So that's a little interactive figure that could be useful. Here's our continuous spectrum. We'll just go through these really quick. Again, given off by a hot object, an emission spectrum given off by a cloud of gas, and then an absorption spectrum given off when white light goes through a cloud of gas. Some colors get absorbed. So here's an example of a spectrum, the sun actually, a star. And so you can see there's a lot of different colors here. This ranges from deep red all the way to purple, to deep purple over here. And you can see there's a lot of gaps. There's a lot of missing colors in here, and that has to do with certain features of the sun. So what can these things tell us about what the sun or anything else is made of? So going back to what we talked about with atoms, this is the hydrogen atom. We talked about how atoms have different energy levels. So there's a certain lowest energy that the atom likes to have. It's a happy atom when it's in its lowest energy, level number 1. And as you give the atom energy, it only goes up to certain values. It can only go up to level 2 or 3 or 4 or 5, etc. If you give it a lot of energy, you could ionize the atom, you could remove the electron. But if you're not going to ionize the atom, if you're going to keep it, the same atom with the same electrons, then the atom can only absorb certain colors. So it can only, certain wavelengths, it can only go up to one of these energy levels. And so every time the atom then loses energy, it goes from one energy level to another. And it can jump. It doesn't have to go from one to the next, to the next, to the next. It can jump. So for example, if an atom goes from level number 5, if a hydrogen atom goes from level 5 directly to level 1, that's a very particular amount of energy, and that will be related then to a very particular wavelength of light, 95 nanometers. If we go from level 4 to level 1, that light would have a wavelength of 97.3 nanometers, and so on. All these colors are in the ultraviolet part of the spectrum. We would not be able to see these with our naked eye, but a special camera could. These are the important ones that we can see. Any color or any transition, any change in energy that goes down to level 2 is going to give off a visible light color. So for example, going from energy level 3 to energy level 2, that's 656.3 nanometers. That's the red color that you see the hydrogen gives off. If the hydrogen atom goes from 4 to 2, then it gives off this color. So you have to give the hydrogen atom energy first to get it up to one of these energy levels, and then it can go down to any energy level below it. And exactly what it'll do, you can't really predict. It's very random. You can talk about the probabilities of what it might do, but you can't predict exactly what any individual hydrogen atom will do. So it's possible that a hydrogen atom will go from level 5 directly to level 1, or maybe it'll go from level 5 to level 2, and then from level 2 to level 1. So the atom might give off this wavelength 434, and then it'll give off this wavelength 121.6. It's possible. There's all kinds of possibilities. But the point is that every single atom has a energy level sort of spectrum like this. And so the changes in energy correspond to very particular wavelengths. And so every atom has very particular wavelengths of light that it can absorb and emit. So these are the colors of hydrogen that we looked at and that we've seen before. And you again can see there's a red, there's a bluish green, and there's some purples over here, bluish, purpley, purple in there. And they get closer and closer and closer together, and there's more of them. They kind of get crowded out. There's more over here that just hasn't been displayed, but they get closer and closer and closer in wavelength because the differences in energy get smaller and smaller. So the ones you often talk about is the red one and the kind of the bluish green one, because those are the easiest ones to see. They're often the brightest ones. This is sometimes called hydrogen alpha, and this is sometimes called hydrogen beta. So here's an absorption spectrum looking at light, visible light, white light going through hydrogen gas. And that hydrogen gas absorbs those colors that it can emit as well. And really, because the red over here and over here is so bright, there might be color, there might be red in here too. It's just that it's not as bright. It looks dark. All right, so there could be some 656.3 nanometer light coming at us, coming through our prism, but in terms of its brightness relative to the colors that are not absorbed by hydrogen, it's not very bright, and so it looks pretty dark. It looks like it's not there at all, but there might be some of those particular wavelengths still coming through. So here's an example of helium, sodium, and neon, and you can see how they're more complicated. Helium has red and yellow and some greens and some blues. Sodium has these two bright yellows here. Neon is more complicated. It has a lot of different colors, a lot of reds and oranges and some yellows. So all the atoms have very unique spectra because of the unique energy levels within them. Now, when you look at an object that's made of a bunch of stuff, you look at the spectrum and you don't necessarily put colors in there, but you look at the absorptions or the emissions, depending on what you're looking at, whether it's a kind of a star that's behind a cloud of gas. You might look at the starlight going through that cloud of gas and look at absorptions by the cloud of gas. Or it could be a cloud of gas that's just giving off its own light, and you might see something like this, an emission spectrum. And so you look at the patterns. You measure these wavelengths and you look at the patterns. These colors are not necessarily blue. The book just labeled them all blue because when you're doing science, you don't necessarily have the colors there. You measure the wavelengths. So what this is saying is that there's a wavelength here of some value, there's a wavelength here of some value that's being emitted, a wavelength here of some value, and so on. And when you match up these patterns, this wavelength and this wavelength and this one 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 and this one, they all match what hydrogen emits. And so you see a particular pattern of lines here that matches what hydrogen gives off. And at the same time, you might see other lines that might match what other atoms give off. For example, here's neon 2+, or +2. That's neon with 2 missing electrons. It's ionized neon. It's missing 2 electrons. This line and some of these lines over here are from helium, regular old plain old helium. There's a couple lines here that are from oxygen, singly ionized oxygen, +1. And so scientists look for these patterns, and they use computers to do it because it can be very complicated. But years ago they didn't have computers, so people had to analyze these patterns, and it took a lot of time. It was not an easy thing to do. So here again is the solar spectrum, and by looking very carefully at what colors are missing, we can determine what kind of elements are in the sun's atmosphere. So we think of the sun as being kind of an object, a very hot object, giving off a continuous spectrum of light. But in fact, that continuous spectrum of light passes through the sun's atmosphere, the outer layers of the sun, and some of that light gets absorbed. And so what actually comes to the Earth is really technically not a continuous spectrum. There are some gaps in the colors, but it's hard to notice that. These gaps are very thin, and unless you had a really sensitive measuring device, you had a spectrum, you had a prism that really spread out the colors so you could see these gaps. Unless you had that, you wouldn't notice it. So in addition to atoms absorbing certain energies and emitting certain energies, molecules do that as well. Molecules are made of atoms, so the individual atoms within a molecule can absorb certain colors or give off certain colors. But there's other ways that atoms or molecules can absorb and emit energy. They can rotate at certain rates. They can rotate at with certain sort of angular frequencies. They can rotate at particular rates, and that requires particular amounts of energy, and those energies depend on the molecule. A carbon monoxide molecule can rotate in certain ways differently from like a nitrogen molecule, two nitrogens, or an oxygen O2 molecule. The rotations are different, and so the energies absorbed and emitted through rotation are different. And also vibration. This might be, maybe this is a carbon monoxide molecule vibrating back and forth, carbon and oxygen. Or you could have oxygen and oxygen. Those two molecules are going to vibrate differently because of the two different masses of the atoms. And so you'll see that in terms of the energy emitted or absorbed by those molecules. And usually these colors, the vibrational colors that you absorb and emit, are usually in the infrared part of the spectrum. Rotations are even further in the infrared part of the spectrum. Some of the vibrations could be invisible in ultraviolet possibly, but usually they're lower energy than visible light. There's not as much energy in terms of vibration, and even less energy in terms of rotation. So here's a molecule, and you can see how kind of cluttered the spectrum is of the molecule. There's a lot of messy stuff in here because of all the possible ways that the molecule can absorb and emit energy through the individual atoms that make it up, or through rotation or vibration, and there could be multiple ways that the molecule could rotate and or vibrate. So here is some questions. So here's that spectrum that we looked at first early on. So which of these features represents absorption? So what you want to look at is, this is continuous. You see it looks nice and continuous, but all of a sudden we get over here, and now we're missing some colors. It doesn't go all the way to zero brightness, but we have some sort of missing colors, missing from the sort of the trend that we were following here. So these would be absorptions by some kind of a molecule or a gas or something. So D is the absorptions. Which of these letters would indicate the greatest intensity of infrared light? So infrared is over here, and somewhere in this region, this wavelength is the brightest infrared wavelength. And so that would be indicated by E. Which letter labels emission lines? So emission, again, is like additional light given off by something. And so that would be these guys over here. There's some atom or molecule in this object that's giving off particular colors. And so these would be the sort of the extra amounts of those colors being emitted. So A would be your emission lines. So what other things can we learn about from light coming from objects, right, besides the chemical and molecular composition? We can also talk about the temperature of objects. So there's something, we talked about this before, thermal radiation. Thermal radiation is related to thermal energy, and thermal energy is related to temperature. Thermal energy is a measure of the total energy at sort of the microscopic scale of a bunch of atoms and molecules that make up something. They're all wiggling around because of their temperature. And the greater the temperature, the greater the thermal energy. And because of all these atoms and molecules wiggling around, they emit light. And that light that they emit, because of their thermal energy, is thermal radiation. So if you look at different objects at different temperatures, it doesn't matter what the temperature is, you give off light. So even a person, 310 Kelvin person, gives off some light. The light is not visible. All right, you couldn't put yourself in a dark room, turn the lights off, and see yourself. you would need a special kind of camera that was sensitive to the infrared light that you give off, because you do give off light. And so this is like the spectrum of light that a human gives off, very long wavelength infrared light that maybe some insects might actually be sensitive to it, but we're not. As you heat up things, if you have a star that's 3000 Kelvin, that star gives off a lot of light, a lot of infrared. As you go from the sort of the deep infrared, the star is brighter and brighter and brighter. There's a particular color where the star is the brightest, still in the infrared, and the star gives off a lot of visible light. Also gives off a decent amount of ultraviolet light, and then eventually the amount of light the wavelength that it gives off kind of tapers off and gradually goes to zero there. But the star gives off mostly infrared light. There's a lot of infrared light that this star gives off. As you increase the temperature, a couple things happen. The area under these curves gets bigger. Notice how the area under these curves is getting bigger. And that area is related to the total energy that the star is giving off in all the different wavelengths of light. So the hotter the object is, just the more energy it gives off, period. But also, the hotter the object is, the more toward the purple, toward the ultraviolet, the brightest color shifts. So for the 3000 Kelvin star, the brightest color is still in the infrared. For the 5800 Kelvin star, our sun, the brightest color is kind of in the greenish, yellowish greenish area. And for a 15,000 Kelvin star, the brightest color is actually in the ultraviolet. So these brightest colors shift toward the purple side of the spectrum in a sense. They could keep going into the ultraviolet the hotter the star gets. This is something called Wien's law. It talks about the shift in the brightest color as temperature changes. So which star is hotter? A blue star, a red star, or a planet that emits only infrared light? Well, you would think that probably a star is hotter than a planet. Usually, that's probably the case, unless it's a very odd planet. But which star then is hotter, a blue or a red? Remember, it's the blue star that's actually the hotter star. Blue, and it's kind of backwards. We should change our water faucets and stuff. H's are usually red, and the C for cold is usually blue. It really should be the other way around, right? A blue star, something that's glowing so hot that it's blue, is a very hot object. Something that's only glowing red, it's a hot object, but it's not as hot as a blue object. So here's another question. Why don't we glow in the dark? You and me, why don't we glow in the dark? So people do not emit any light, any kind of light at all? That's not true. They do actually emit light, and you can detect it with a sensitive enough camera, sensitive to infrared light. People are too small to emit enough light for us to see. No, we're pretty big. If we got hotter, we'd emit plenty of light to be able to see with our eyes. People do not contain enough radioactive material. Well, it doesn't come from the radioactive material. It just comes from the jiggling of our atoms and molecules and the electrons that make us up. So it's B. People only emit light that is invisible to our eyes. We only emit infrared light. So again, here's that same thing that we looked at. How do we interpret this? We'll go through this again now that we have a sense of these different spectral features. So when we look at this thing, we see that it's, whatever this is, it's giving off a lot of red and not a lot of blue. All right. So, and if you compare the spectrum, it looks very much like what you would see from the sun, except you're missing the blue. And so this is some kind of an object maybe that's reflecting sunlight, but the blue part of that sunlight is getting absorbed. And so the light actually looks kind of red that's coming off the object. It's a red-looking object. And then we've got this thermal radiation. The object has a certain temperature. It's giving off light because of its temperature. And if you look at the way you think about thermal energy, thermal radiation, the peak wavelength is in the infrared. That indicates an object that's fairly cool. And if you measure exactly what this brightest color is, you find that that's an object that has a temperature of about 225 Kelvin. It's a fairly cold object. So it's reflecting a lot of red light, and it's a fairly cold object. It's giving off its own light, but that light is in the infrared part of the spectrum. Then we have some absorption. These particular colors that are absorbed indicate that there is a molecule, carbon dioxide, in this object. So maybe it's an object that has like an atmosphere of carbon dioxide. So it's emitting infrared light, but some of that infrared light's getting absorbed by the molecules of carbon dioxide in its atmosphere. And then finally we have ultraviolet emission of something, and that often can indicate something that's hot, and it could be we could try to figure out what kind of molecules these would be, or atoms these would be, but these could be things that are in some hot area, maybe the upper atmosphere of something. Oftentimes the upper atmosphere of planets are very hot. So it turns out this is the spectrum of Mars, or at least approximately. There's a lot more detail to it than what we have here, but we don't need to go into all that detail. So that's Mars. So before we go into the Doppler effect, the last topic of this chapter, let me just show you a couple more of those interactive figures that are useful. Here is the one that we've seen before. We can talk about atoms again giving off their own energy, and so this atom is in its lowest energy state, level 1. We can excite the atom, it'll jump up into energy, and then it'll come right back down again and give off some light. And it does it kind of randomly, and you can kind of see the spectrum starting to get built up down here. So this is kind of fun to play with. The whole process is very random. We give the atom energy, and it kind of randomly goes down in energy and gives off light of various colors, various wavelengths. But again, there's only certain specific energies that it can be at, and therefore only certain specific colors that it can give off. This interactive figure shows this thermal radiation spectra, and so here we can adjust the temperature of an object, and so here's the temperature that we have it at this point, 2.24 times 10 to the 3, that's 2,224 Kelvin. The brightest wavelength is somewhere over here, and it gives it to us here, 1.3 times 10 to the minus 6 meters. So that's like 1,300 nanometers. So that's definitely in the infrared part of the spectrum. If we increase the temperature, the total area under that curve is increasing, indicating a much greater energy overall. But also the peak wavelength, the brightest wavelength, is now in the ultraviolet. And so this is 1.9 times 10 to the minus 7. That's 190 nanometers. So that's more of the ultraviolet part of the spectrum. If we bring it back down so the peak is in the visible, somewhere like this maybe, right in there perhaps, something like that. Here is a peak of 6.57 times 10 to the minus 7. That's 657 nanometers. That's red. That's a peak in the red part of the spectrum. That's a star that's 4,410 Kelvin. A little bit cooler than our sun. See, this is fun to play with. You can kind of pick your temperature and play with that a little bit. And then there's another one. We'll come back to this in a minute. This one and this one, yeah. And then I've talked about these PHET simulations before. There's a good one there about black body radiation. If you look for it here, black body spectrum. If we go to that really quick, this is kind of nice. So this allows you again to change temperature, and it shows you the spectrum again, plotting brightness and wavelength. And so here's a 4,800 Kelvin star, and you can see the brightest color is in kind of the greenish yellow part of the spectrum. So if I increase the temperature, the area under the curve gets bigger. So where's 5,800? There's our sun approximately. The brightest color is kind of the greenish part of the spectrum. And this star gives off a lot of infrared and some ultraviolet. This ultraviolet is being emitted as well. That's what gives you your suntan. And so it shows you that that's how hot the sun is. A light bulb filament is around this temperature, about 3,000 Kelvin. That's pretty typical of a regular light bulb filament. And you can see a light bulb gives off some visible light, which is good. That's why we use them. But they give off a lot of infrared. The peak wavelength is in the infrared part of the spectrum. So regular incandescent light bulbs don't give us a lot of the light that we want. They give us some visible light, but most of the energy that they give off is in the form of infrared light. Not very useful for seeing around the house, but maybe useful for warming up the bathroom in the wintertime perhaps. So this is another good simulation that you could use, you could look at. So the last thing to talk about is what happens when sources of light move. How do we detect the motion of a star, for example? Well, if you have a train, for example, giving off sound from its horn, the siren up here, it goes off in all directions. And there's a wavelength of sound for sound waves. And so an observer behind the train and an observer in front of the train, if the train's just sitting still, they'll hear the same exact sound. They'll hear the same exact pitch. They'll measure the same exact wavelength. But if the train is heading toward them, these sound waves start to get kind of compressed in the direction of the train. As one sound wave is produced, the next one is produced closer to the last one. And so the wavelength in the direction that the train is moving, it gets shorter. The wavelength in the direction opposite that which the train is moving is getting longer. And so that's called the Doppler shift. And so if there's an observer and there's a train coming toward the observer, they'll hear a sound that has a shorter wavelength or a higher frequency, a higher pitch. And somebody that's behind the train is going to hear a sound with longer wavelength, lower frequency, a lower pitch. Same thing is true for light. If this light bulb is giving off light and it's traveling towards somebody, all the different colors that it's giving off are going to have shorter wavelengths for this person over here who the bulb is traveling toward. This person over here who has the light bulb traveling away from him is going to measure longer wavelengths for all those different colors. And so that's going to be true for any source of light. If the source of light is traveling toward you, all the colors you see are going to have shorter wavelengths. If the light bulb or the source of light is traveling away from you, all the colors you see are going to have longer wavelengths. So here's again, the hydrogen spectrum. Red, it's a very particular red, greenish blue, and purplish blue sort of colors coming from hydrogen. If you notice that all those colors are slightly shifted, we say they're shifted toward the red part of the spectrum. See how this red is a little bit more red. This greenish blue is maybe a little bit yellow. And this blue is maybe a little bit lighter blue in a sense. So these colors have been shifted toward the red. We say that it's been red shifted. That indicates longer wavelength, which means for every one of these colors, a slightly longer wavelength. That means the object is traveling away from us. And if the shift is bigger, if this blue shifts to this kind of bluish green, and this greenish color shifts to this yellow, and this red shifts to this much deeper red, that's a bigger shift toward the red. That's a bigger red shift, we call it. That indicates a bigger velocity moving away from us. And so the bigger the shift in the colors that we measure, the bigger the velocity of the object away from us or toward us. And these are two examples of objects traveling toward us. The red color gets shifted more into the orange for some low velocity toward us, but the red could get shifted into the orangish yellow even if the velocity toward us is even greater. So the Doppler shift is a measure of the shift of a wavelength from its sort of laboratory position to the measured position, and that indicates some velocity of the object either away from us or toward us. So the amount of the red shift or the blue shift tells us the object's speed away from us or toward us. Now, there's a complication, because if the object's moving kind of perpendicular to us, we don't measure any red shift. We don't measure any blue shift. And so when we measure the shift, all we're really measuring is the amount of the motion along our line of sight. And so if the object is moving entirely along our line of sight, then the shift that we measure will give us exactly the object's velocity. But if the object's kind of moving in a different direction, this object is moving kind of down and away, not just directly away from us, but there's sort of a component of the motion that's away from us as well as perpendicular to the line of sight. We'll only be able to measure sort of part of the motion of that object, not the object's full speed. We can only get some information about the object's velocity away from us. So if you measure a line in the laboratory, let's say you measure a spectral line, a color that's 500.7 nanometers in the laboratory, and then you find that same color, that same line in a star, but it has a slightly different wavelength. You measure it to be 502.8 nanometers, so it technically doesn't look like the same color, but it fits in the same pattern that maybe comes from a particular atom. So it's slightly shifted to a slightly longer wavelength. What can you say about the star? So the wavelength has been shifted, it's gotten a little bit bigger. When wavelengths shift to bigger wavelengths, we say that they have been red shifted, and that's an object traveling away from us, right? The object's traveling away from us. So we can also look at rotation. If an object rotates, when we look at a spectral line, part of the side of the object, the whole object's giving off this particular color that you might be thinking about, but one side of the object is kind of moving towards you while the other side is moving away from you. And the middle of the object is kind of not moving toward you or away from you at all, perhaps. And so there's different parts of the object that are moving at different speeds toward and away from you. So one spectral line actually gets spread out into multiple lines. And this is kind of deceiving. It doesn't necessarily get spread out so much that it looks red and yellow and blue. But what it's saying is that there's a particular color that you're trying to look at, and the whole thing actually gets spread out. Some of the spread towards shorter wavelength indicates that part of the object is traveling towards you. Some of the spread toward the redder, longer wavelengths indicates that part of the object is traveling away from you. So here's a star. The star is giving off a particular color, and maybe it's a yellow color. But this part of the star that's traveling away from you, that same yellow color is getting shifted toward longer wavelengths, and so that color might actually look more toward the red part of the spectrum. Whereas the star over here, the part of the star over here, is kind of heading towards you, and so the same yellow color that the star is giving off actually gets a shortened wavelength because the star is moving towards you. Up here, the surface of the star is moving towards you. So the entire color that you would see here, which should be yellow in the middle there, actually gets spread out. And really, you won't see it spread out this badly, where yellow actually becomes blue or becomes red. You'll just see a slight spreading of the color. And the very center of that spectral line is the color that you would have if the star were not rotating at all. But because of the rotation, you actually get that color plus shorter wavelengths, a little bit shorter wavelengths, and a little bit longer wavelengths. There's a little animation to kind of show you this. Again, going back to the interactive figures. So here's a star. Well, actually, this doesn't show the rotation, but it shows the Doppler effect. So this star is just sitting there. It's giving off one particular color, let's say in all directions. We can select it and make it move away from us. And so the star is moving away from us, and so the wavelengths get longer. So if there's a part of the star, if the star is rotating and just a part of the star is moving away from us, the light from that part of the star will get redshifted. If the star is moving toward us, the light gets blue shifted. The light looks a little more blue. And so again, if the star is actually rotating, part of the surface is actually moving toward us, so light coming from that part will actually get blue shifted. So, to summarize everything, it's a long section, but there's a lot of information here. The three basic types of spectra are the continuous spectrum, the emission line spectrum, and the absorption spectrum. And for each of those spectra, we can understand them by thinking about how light is emitted by atoms. Each atom gives off a very specific sort of fingerprint of colors. They emit those colors and they also absorb those colors. And so we can identify the kinds of atoms that something's made of by looking at the emission or the absorption in that object spectrum. And then we can look at temperature of objects and we can think about what's the brightest color given off by that object. We look at that sort of pattern of thermal radiation and look at the brightest color, and that tells us the temperature of the object. And then we can tell the speeds of objects by looking at how colors are shifted left or right toward the red or toward the blue. We look at patterns that we recognize from laboratory studies as belonging to certain atoms like hydrogen or helium. And by realizing that those patterns don't match exactly the colors that we see in the laboratory, we can measure the shift in the wavelength of those colors. That shift in the wavelength ultimately tells us the speed of the object, but again, it's only the exact speed if the object is definitely moving directly away or directly toward us. If the object's moving at some angle relative to our line of sight, then we can only measure like sort of a minimum of what the speed is. The speed is definitely bigger, but we can't measure the full motion of the object. So that wraps up Chapter 5. A lot of information, but I encourage you to look at the interactive figures in the D2L site and play with those, and also go to that PHET site and play with some of the animations, the black body radiation and so on. So have a good night.